This is around my ear, that kind of thing? Or is it this ear?
Yeah, I think this is.
This ear?
People use that one.
People use the other ear?
No, this one.
This one. Yeah.
This is then going up.
Oh, cool.
Three
Okay.
blackboards.
Great.
Okay, excellent. So welcome to the last lecture series, which will be by Nima. And the plan is now to go until roughly 8. Then we will have a pizza, which will be coming. We will have a break for a little later dinner. And then after that, Nima will continue until 10:30. We will have another break with some snacks. And then afterwards, there will be kind of free evening. Yeah, you will go.
Okay,
Okay.
You can keep dropping exponentially. It'll be okay. It'll be fine. Last person standing gets my, I don't know, my impressiveness, beingness. That, gosh. All right. Well, I'm very sorry for mucking around with the schedule today, but you can blame Austrian Airlines. By the way, first of all, apologies to anyone who might be offended by this shirt. I don't know if anyone is or isn't offended, but someone spilled all their coffee on me in the airport in Vienna, so I needed a shirt. That says something about how many shirts I brought, by the way. But anyway, so anyway, I have no idea if there's any issue between Australia and Austria, but it was either this shirt or something with Mozart on it, and you know, I prefer Beethoven, so that. All right, so I have a few hours less than I thought to tell you something about this sort of general subject of positive geometry and amplitudes, and of course it's going to be impossible to do something really, really systematic, completely start to finish. I think the sort of closest that I've come to trying to give a systematic accounting of at least part of the subject, the part of the subject that's closer to n=4 super Yang-Mills and the amplituhedron, is in a semester-long course I gave when I was on sabbatical at Harvard back in 2019, which the good folks at Harvard actually put online. So if you do want to see in a great deal of more gory detail an introduction to the positive Grassmannian, the amplituhedron, and so on, it is in that course. But what I thought I'd do today is at least give you some sort of contentful, non-trivial highlights about some of the sort of central ideas that have been emerging in this connection over the past 10 years or so. And the plan before dinner is to first say some very general things, very quickly about the philosophy, a few things about how functions, or more precisely forms, can be connected to geometric spaces via the sort of notion of canonical forms or forms with logarithmic singularities on the boundaries of some space. And then do the simplest example. It's ahistorical because ironically it took some time to understand the simplest example of just the very simple scalar, colored scalar theory, trace phi cube theory. At tree level, where the positive geometry is the famous isosahedron polytope. So that's in many ways the very simplest example where we can see some of these ideas in action. And then after dinner, I'll switch to telling you about still in my view the much more deeper but still more mysterious avatar of these ideas in the context of gluon scattering on n=4 super Yang-Mills in the story of the amplituhedron. Again, it will not be a completely systematic introduction to the all aspects of the subject. In particular, right now I'll only be telling you about trace phi cube theory at tree level. I'll be giving a rather different point of view about that general subject and its extension to all loop orders in my talk at Amplitudes on Monday. Okay, so there will be very little overlap between this way of thinking about things and the picture that you'll get on Monday, which will be an entirely combinatorial one. But nonetheless, I think you'll be getting enough of an idea of what is going on. Okay, so again, I will try to give you some at least precise definitions, not just a lot of blah, 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 and a few non-trivial moving parts in this set of ideas. So if you haven't worked on these things before, I hope it's an invitation to sort of look at what's going on in what certainly appears to me to be a kind of a fascinating set of ideas. Okay, so to begin with, we have this, the kind of a very big picture is that we know that we're interested in scattering amplitude. Scattering amplitudes are a classic, maybe the first classic example of an observable that's not a local observable. A scattering amplitude is not something that you measure at points in space-time or in the neighborhood of points in space-time. It's an asymptotic observable where things come in from infinity, they crash into each other, and they go back out to infinity. And as such, unlike local observables that are even labeled by points in space-time, scattering amplitudes are not labeled by points in space-time. They're labeled by on-shell momenta. And the on-shell momenta you can think of as actually labeling points in asymptotia. Okay, so the data that labels a scattering process does not live in the interior of space-time. It labels things on the boundary of space-time. Nonetheless, and you know, this is very vivid to an experimentalist. When you collide two protons at the LHC, you're colliding them, you know, the ring is 27 kilometers around. 27 kilometers is pretty close to infinity compared to the size of the proton, which is 10 to the minus 14 centimeters. And all you know is happening is that the protons come in and some stuff comes out. And that's all you know. All you have is this sort of information that you measure at infinity. And yet we tell a story for what happens to give rise to the pattern of amplitudes that involves the pictures of local processes in space-time in some way. So we're supposed to draw these diagrams. Each diagram represents some local process in space-time, and we're supposed to add up all the possible ways that the process could have happened in order to be compatible with the principles of quantum mechanics. So there's kind of a, if you like, before we do this, there's a question mark, there's a black box. Something generates these very interesting amplitudes, that have very intricate analytic structure and all these properties. Some black box is generating them. They're not. There has to be some structure that gives rise to them. They're not trivial functions. And the usual answer for what that structure is invokes some things that are not there in the problem. They invoke some auxiliary space. It invokes the interior of space-time and a Hilbert space in which the sort of wave function is evolving. So the interior of space-time and Hilbert space are auxiliary constructs for producing the final answer, which doesn't actually know about those things. The final answer is just labeled by a bunch of on-shell momenta. So the sort of the moving question of this point of view about trying to understand amplitudes is to fill in this with something else, okay? So we want a different kind of question, and ideally this question will be formulated directly in the kinematic space where the amplitudes are defined. And as we'll see, we'll eventually get there, and all the examples that we'll talk about, in this first example, we'll talk about icosahedra and so on, we'll be there right away. When we talk about amplituhedra, we'll actually have to first take a step into another auxiliary space for a little while until we see what's going on directly in kinematic space, okay? So, but in the end, there is a story directly posed in kinematic space. No auxiliary structures whatsoever, directly posed in that kinematic space. And that's what we're looking for. We're not looking for, you see, in this, a lot of what drives progress in thinking about amplitudes very correctly is seeing the simplicity and structure in the answer and trying to find better ways of calculating the answer and exposing that simplicity and structure. And that's fantastic, and it's a sort of fundamental engine of progress in this business. But the ultimate goal of this thread of work is not to calculate the answer. It's to find a different question. It's to find a different question to which the amplitudes are the answer, okay? And of course, one of the huge clues that such different questions exist is that the final answer looks so different from and so much simpler than what you'd naively be led to expect by thinking about summing over all the Feynman diagrams. All right, so we're going to be looking for a new kind of question, and it's clear ahead of time that this new kind of question will involve new physical ideas and new mathematical ideas. That's sort of a given. I think that's obvious ahead of time that it has to involve both kinds of novelty. And that's what we're going to be talking about. Now, the main physical idea is very familiar in the amplitudes business, but as an extreme version of the on-shell philosophy. We just never want to talk about virtual particles. Okay, so that's part of the mantra of looking for a question in kinematic space. It's an on-shell kinematic space. So we're going to be looking for a question in on-shell kinematic space whose answer is our amplitudes. And the kind of one of the emerging picture. So, and what's the challenge? What's the challenge? The challenge is that this space that labels the kinematics of scattering processes, it just seems too boring. It does not seem like an exciting enough place to be able to ask any interesting questions. Okay. So, what is the kinematic space? Well, there's lots of ways of talking about kinematic space. One of them is give me n on-shell momenta. Let's say we're talking about massless particles, n null momenta. That's my kinematic space, the space of n null momenta. Or maybe you want to work in terms of Mandelstam invariance, especially if you're talking about scalar theories. Maybe you want to talk about the space of dot products of pairs of momenta, because the amplitude only depends on them. So that's another way of thinking about kinematic space, dot products of pairs of momenta. Okay, there's roughly n squared dot products of pairs of momenta if you have n particle scattering. Again, what the heck are you supposed to do in this space of n squared variables, right? But that's our space. We have to learn to ask some question in that space. Or you could think about it more geometrically, like what's the boundary of Minkowski's space look like? Well, you shoot a light beam out to infinity and it hits a point on the celestial sphere. Okay, so that's another way, yet another way of labeling the on-shell data is in terms of the energies that particles have in the directions that they hit on the celestial sphere. Okay, so that's the kind of celestial amplitude program, so think about amplitudes from that language. Or you can think about labeling them by twistor variables. None of this makes any difference as far as the sort of main problem, which is that we don't know what to do when we go there. Okay, so we go to the space of n null momenta, now what? Okay, you have to ask a question in the space of n null momenta whose answer is all the richness and complexity of scattering amplitudes. This is to be contrasted to what people have been doing with great guns in anti-de Sitter space, where if you go to the boundary of anti-de Sitter space, what you're left with is a perfectly ordinary space. It's a perfectly ordinary flat space in one lower dimension. It has a notion of locality, it has a notion of time, it has a metric. And so once you get, of course, it's a huge deal to get into this sort of, you should care about boundary observables, sort of holographic mindset. It's a big deal to get into that mindset. But once you're in that mindset, there's a very natural thing you could do in the boundary of anti-de Sitter space. Talk about a local quantum field theory that lives there. There is no such thing as a local quantum field theory that lives on the space of n null momenta. Okay? That's our problem. Or even if you think about it more geometrically, in terms of the celestial sphere, it's clear that whatever the heck this theory is that might live on the celestial sphere has no ordinary notion of locality at all. Okay? Definitely doesn't have an ordinary notion of time or of locality. Or if you go to twistor space, that's another wonderful place you go. What should you do in twistor space? Should you write down a Lagrangian? Feel free. You can write down a local Lagrangian in twistor space and you'll get a massive crap non-local theory in space-time. Okay? The reason we write down Lagrangians and so on as our first instinct is because we have locality in the spaces that we care about. And again, there's no good notion of locality or time or anything like that for the thing that we care about. So that's why necessarily the things that we're going to do are going to involve more guesswork and are going to be a little more adventurous. Okay? So we don't know ahead of time what the ab initio rules are, and so we have to discover them. Okay? So that's the... All right, so, but the kind of emerging picture, at least in one in the one direction that we've been exploring, is that even though this kinematic space seems really arid and kind of boring and dry, that inside it, there are certain combinatorial ideas, most primitively, that give rise to some geometric structures. So these are these positive geometries. And these are really sort of big generalizations of polygons. Okay, so there are regions in space, in some space, that have boundaries of all codimension. That's the important thing about them. So a polygon is a good example of a positive geometry because it has boundaries that are edges and vertices, but a circle is not. Okay, a circle has a codimension 1 edge, but it doesn't have any vertices. Okay, so there are objects that have boundaries of all possible codimension. Associated very closely with these positive geometries are these canonical forms. There are now, these start being analytic ideas. So this is not just some geometric space, but there's some sort of form that lives on kinematic space that's completely determined by, entirely determined by, the requirement that it has singularities of a prescribed type on these geometries. And this is related either to tree amplitudes or to the loop integrand, when that notion makes sense. Not the actual amplitude, which you get after loop integration. And of course, if you do manage to integrate the canonical forms, then this is what's going to keep going to polylogarithms, symbols, maybe non-perturbative things, and so on. Okay, but we're going to sort of stop at around this point for most of the discussion today. Okay. In my talk on Monday, we'll talk about full amplitudes as well, and we'll see that. I mean, there are other arrows here, and perhaps maybe one of the most surprising things to me in this whole business is that it's not even really geometric structures that are fundamental. It's really combinatorial ones that are the most fundamental of all, and we'll see some examples of that today as well. All right, but in the spirit of not doing something super systematic, which I won't be able to do, I want to jump in and tell you something about what these positive geometries and canonical forms are, because that's the sort of first thing to get you some feeling. We're going to be discovering in a moment certain sort of shapes that live in kinematic space, naturally live in kinematic space, but I want to imagine that some shape is given and tell you how you get an amplitude from it. So I want to tell you how you would connect a function or a form to a shape. By the way, it goes without saying, please interrupt at any time. I don't have any especially fixed agenda. We could slow down exponentially, we could speed up. We could definitely speed up exponentially, but we could definitely also slow down exponentially. I'm happy either way. Okay, so what's the first example of, so first let's do some examples of positive geometries. And again, the easiest examples are just like in one dimension is like the inside of an interval. So let's say this space is X, and it's the inside of the interval between A and B. Okay, so in this case, the positive geometry is the interior of the interval between A and B. Or I could be in 2 dimensions, and it could be the interior of this triangle. Again, the important point is that it's, maybe this is the X plus Y equals 1 is that line. Or it could be like a general quadrilateral in 2 dimensions, or maybe a pentagon. Okay, so these are polygons, and more generally, you could have in higher dimensions a region that's cut out by a bunch of linear inequalities. Okay, so you have to just have a bunch of linear inequalities positive, and if they're not inconsistent, if there is such a region, those are called polytopes. That's one definition of polytope, is a region that's cut out by a bunch of linear inequalities. There's a second definition of polytope. So in this case, the interior of this square is cut out by that, that line being positive, that linear equation being positive, a bunch of 4 linear equations being positive. That's one way of cutting out the inside of the quadrilateral. Another way of characterizing the inside of the quadrilateral is centered on its vertices rather than its facets. Okay? And here you say that you have a bunch of vertices, and you look at the convex hull of those vertices. And what that means is you just take a weighted average, like the center of mass idea. You imagine there's masses for each corner, and you vary all the masses and see what the points end up being. Clearly, as you vary all the masses, you're going to span over the entire interior of the space. Notice that in both definitions of a polytope, some notion of positivity is central. In the inequality definition, it's a bunch of linear inequalities bigger than 0. In the vertex definition, it's a weighted sum with positive masses, with positive weights. Okay? So there's a notion of positivity which is there in both cases, and that's where the positive in positive geometry comes from. Okay? Is that there's a notion of positivity built into their definition. And this is a general fact about polytopes, by the way. They have sort of 2 dual presentations. One in terms of a bunch of linear inequalities, and the other in terms of the convex hull, which has to do with the facets of the polytope. The other one is the convex hull of the vertices, which is a sort of opposite extreme. So there's a definition involving the highest codimension facets and a definition involving the lowest codimension, the vertices facets. Okay, so that's what these spaces are geometrically: interval, triangle, square. But now we're going to do something a little more interesting. We're going to associate with this shape a certain differential form, and that differential form is such that you have singularities on the boundaries and all the boundaries of the space. Okay? Now, what do I mean by this precisely? First of all, let's just think about what it means for a form to have singularities. Let's say I give you the form dx. Okay? This form clearly seems to be non-singular everywhere. It is non-singular everywhere around x equals 0. It does have a singularity at infinity, okay? Because if you switch variables to x is 1 over w, then this is minus dw over w squared, okay? So that has a singularity in your w equals 0. But these are singularities that by doing changes of coordinates, you can remove them, okay? But there is a particular kind of singularity that you can't do that for, which is what? Just dx over x, right? So if you take dx over x, this is something that no change of coordinate can sort of remove the singularities. And it's because it doesn't just have a singularity at x equals 0, it has a singularity at x equals 0 and x equals infinity. And this is unlike dx, which is just d of x, or dx over x squared, which is d of 1 over x. Those are the d of something rational. This is not the d of something rational. This is the d of log x. So that's why this is called the d log form, in this case, literally d log x, okay? But these d log forms are really genuine singularities, and you can detect them by doing a little contour integral of the form around the place where it has around x equals 0, for example. Okay? If you do a little contour integral, you'll get 2 pi I, or 1 if you normalize by the 2 pi I. So going back to this example, we can now ask, is there a form that has logarithmic singularities on the boundaries of this interval? And okay, well, this is easy enough that we can do it. And what's your sort of first guess for what it would be? Your first guess would be dx over x minus a, right? That has a logarithmic singularity at x equals a. And there should be something with dx over x minus b to have a logarithmic singularity at x equals b. And super naively, I would put a plus sign before thinking about anything. Okay, they're obviously on an equal footing and so on. But there's not a plus sign there. There has to be a minus sign. And can anyone say what's wrong with the plus sign here? Anyone who hasn't heard me explain it to them before? So you don't look artificially prescient. All right. Everyone is still shy. So what's wrong with the plus sign is that this form certainly does have a logarithmic singularity at x equals a and x equals b, but it also has a logarithmic singularity at x equals infinity. Okay? And if you look at the form, indeed, it looks like 2 dx over x at infinity. And so it also has a singularity here at infinity, right? Now we don't want that. We want a form that has logarithmic singularities on and only on the boundaries of the space. Okay, so that tells us that we need to have a minus sign there. And we also learned that these forms, these so-called canonical forms, are sort of defined up to orientation. Okay, so there's an overall orientation of the surface. All right, let's go back to this example. Now, here, what would the form be? Well, again, the most naive thing is you put the poles that you see, right? So there would be a dx over x, y, and maybe 1 minus x minus y. Okay? And this is the correct form of logarithmic singularities. But it does a little bit more than, actually a lot more, than just get the correct codimension 1 boundaries. And this actually goes to the heart of the definition of canonical form. So let's say we go on the codimension 1 boundary where x equals 0. Okay, so that would localize us here. Okay? Now at the level of the geometry, now we have a new positive geometry, namely this interval, which we just talked about before. Okay, that's a perfectly good positive geometry. So what you want is that if you take a residue of this form on the locus that takes you to one of its boundaries, that the corresponding residue should be the canonical form for the boundary. All right, so, and in this case, is it? Well, let's say we take the residue at x equals 0. You could imagine either doing a little contour integral in your head, or even more dumbly, just erasing dx over x, and setting x equals 0. So if I take the residue of omega at x equals 0, I go from a 2 form to a 1 form, and what is that 1 form? It's dy over y, and I have to put x equals 0 here, so it's 1 minus y. Right? And this is indeed the canonical form of this interval, including the minus sign that we talked about before. Okay, because I can write that as dy over y minus dy over y minus 1. Right? Or another way of saying it is that there's no singularity at infinity here. It's dy over y squared. Okay? So that's the interesting thing about the canonical form, is that when you take the residue, and that's why it isn't just given by the first poles. When you take a residue on the residue, tak, you have to get you get a new positive geometry, and the residue of the form has got to be the canonical form for the boundary. All right, and you can easily check the other examples in this case. So in this case, doing the dumb thing and just shoving the 3 poles that you see from the picture just works, and it gives you the correct answer. And this works for any simplex in any number of dimensions. Okay, so if you have a tetrahedron in 3 dimensions, any simplex in any number of dimensions, this is going to work. The square is already a much more interesting example. And let me draw the square in a way that'll make my life easier. So this is my square. Okay. Here are my points 1, 2, 3, 4. And let's just say that there's an equation. The equation for this line is, I don't know, let's call it L1, or I guess they call it L12. But let me call it L12, L23, L34, and L41. Okay, is it clear what I mean by that? I mean, those are literally the linear equations that are associated with each one of those lines. Okay, so the quadrilateral is defined by each one of the L12 is like ax plus by plus c, and they're defined by L12, L23, L34, L41 bigger than 0. Okay? So now what is the form? Well, the first guess you'd make again is dx dy over L12, L23, L34, L41. But this can't be right. Okay? This can't be right because, you see, let's say I take a residue on where L12 is 0. All right? So I want to take a residue where L12 is 0, which means that I have to end up here on that line. So after I take the residue, I'll have some omegas, maybe I get rid of x, I have y, but I'm just parametrizing this line in terms of y, it doesn't matter. But I still have L23, L34, and L41 downstairs where I've evaluated this on L12 equals 0. Okay, so they're just now some linear functions of y. Okay, if I solve for, but where can this form have singularities? Okay, this form can have singularities now either where L23 goes to 0, L34 goes to 0, or L41 goes to 0. Now, so I'm already on L12 equals 0. So the singularity where L23 goes to 0, that's welcome, that's good, that's this point 2. The singularity where L41 goes to 0 is also welcome. That's this point 1. But the possible singularity where L34 goes to 0 is not welcome. Okay, that possible singularity is up at this point star, and that's not part of my geometry. Okay? Similarly, there's another bad point here. That's another bad point. Again, it's clear. We have 4 poles in the denominator. There are 4 choose 2 equals 6 possible places where pairs of them can intersect, but our geometry only wants 4 of them. Okay? So this can't be the answer. So what do I need? I need some factor in the numerator. Okay? And what is the job of this factor in the numerator? It has to go to 0, both at this point and at that point. Okay, well, it's very easy to make something that's 0 at those 2 points. It's just the equation for the line that joins them. Right? So there's this numerator, which is actually the line that joins 1, 2 intersect 3, 4, and 2, 3 intersect 4, 1. Okay? And that is the correct canonical form. Okay? So here we're just directly using the definition of canonical form, and we see already it's a little non-trivial. There's an interesting numerator for the case of the quadrilateral. Let me actually just keep going for a moment to talk about the pentagon, just so you see that even in these trivial cases of polygons in the plane, life gets interesting quickly. So for the pentagon, we draw a picture that makes people on the plane think you're a Satanist. Okay? Maybe they're right. Okay, so that's the, yes, sir.
What if you, in the previous case, took the sum over 1 over 2 adjacent L's?
That would not do it. The sum that won't do it. Yeah, that would not really kill. You really want a 0 on those bad points. The moment you get a 0 on the bad points, you are done. Because then the fact that all the but if you just took the sum, if we just took a yeah, I think in just hold on to that thought for a second, because that's going to be one of our triangulations actually. Okay, so yes, as you'll see, it starts getting harder to guess as we go to higher points. So in this case, there are 5 bad points. Okay, so these are there are 5 propagators. 5 choose 2 equals 10 possible places where pairs of them can meet. 5 of them are good, 5 of them are bad. These are the 5 bad ones here. So now what do you need for the numerator? You need something that vanishes at 5 points. And 5 points determine a conic. Okay, so there's in fact a unique conic that passes through 5 points. Okay? And that's the numerator. Okay? It's the 5 points that pass through this conic. And that actually works for any polygon. Okay? For any polygon, you can directly just use this definition of a canonical form to determine the numerator. And the numerator is this very interesting object that's this higher and higher degree polynomial in the variables that goes through, that's fully determined by going through more and more bad points. Okay. Now, but coming back to this example, but I should say that, so this already shows that there is something kind of rich in finding these canonical forms, even for these really trivial examples. But this is too complicated a procedure, at least so far. I should say there's a kind of a mathematical theory for these numerators that we didn't know about until a few years ago, and that the mathematicians who'd been developing had no idea it had anything to do with canonical forms. But there is a very interesting sort of object that people call adjoints of polytopes that turn out to exactly be about these numerators. Okay, so finding these interesting loci of zeros that are determined by the object that you're talking about. But at the moment, it looks like they know about as much about it as we do. It's not well developed yet to take a random object and sort of just directly write down its corresponding numerator. In a paper, I don't know, 5-6 years ago with Andrew Hodges and Yera, we did work out this strategy for determining the numerators of like NMHV tree amplitudes at n equals 4 super Yang mills, say. So there you can do it. Up to that point, you can actually directly determine the numerator. No triangulations, no BCFW, nothing. So it's just a sort of direct way of determining the numerators. But so far, the most practical way of getting these canonical forms is via the idea of triangulation. Okay, so let me just say this. So let's say you have the canonical form. So let's say you have this quadrilateral. Then imagine that you break up the quadrilateral into two pieces like that. Okay? Then what would happen if we sum the canonical form for this guy? Well, let's just look at the canonical form for this guy. The canonical form for this guy has logarithmic singularities, well, on the boundaries of this triangle. The canonical form for this guy has logarithmic singularities on the boundary of this triangle. In particular, both of them have a pole or a logarithmic singularity here on this internal boundary that's not actually there in the actual geometry, right? However, if I add the canonical forms, so let me just write this as one, if I add the canonical form for the triangle 1, 2, 3, plus the canonical form for the triangle 1, 3, 4, and remember these are even oriented, so there's a sign, so I'm choosing the orientation sort of carefully here. Okay, so that's oriented like that, that's oriented like that, so that the sort of orientations here and there are opposing. Now, here's the cool thing, that the residue on this internal boundary is now 0. And why is it 0? The sort of beauty of positive geometries is that when you get to a boundary, the form that you have is just a canonical form for the boundary. It doesn't know where it came from, right? This could have been some other gigantic polygon of something else. It could have been something else. Okay? But it doesn't matter. On this side, by the time you take the residue, the whole point of the canonical form is you just get the canonical form for that interval. And similarly from the other side. And therefore, if you add them with the correct signs, they're guaranteed to vanish. Okay? And that's the kind of logic of the argument why if you triangulate some region and add up the canonical forms for the pieces of the triangulation, that you can get that you triangulate the whole object, okay? So now this makes you kind of think of the notion of volume a little bit. It's like taking the thing and breaking it up into a bunch of pieces. And I want to emphasize this is not, these things are forms. They're not numbers, they're not scalars, they're forms associated with each piece, okay? So these are not volumes yet, but they're achingly close to volumes. And in a moment, we'll see that they're literally dual to volumes. Okay, so let's just not get there yet. At the moment, all we know is if we triangulate any way we like, and the sum, the pieces. If the pieces are simple, if the pieces are triangles, then the sum is going to give us the canonical form for the whole object. Of course, the disadvantage is that there's nothing unique about the triangulation. I can triangulate this way, I can triangulate that way. There's lots of ways of triangulating the object. But every triangulation into simple pieces gives you some representation of the canonical form as a sum of simple pieces. Okay, so jumping ahead in the applications to amplitudes, amplitudes are, in this business, the canonical form of certain geometries. In the simplest cases, like scalar theories, they're literally canonical forms of polytopes. And those polytopes are things like isosahedra and their generalization that we'll just talk about in a second. For n equals 4 super Yang-Mills, they're the canonical forms of sort of curvy versions of polytopes, and those are the amplituhedra. They're sort of curvy versions of polytopes where the equations that cut them out aren't linear. Okay? So that's why they're richer and still more mathematically mysterious. There's still a lot more to understand about them. But in both cases, you want to break them up into simple pieces, the analog of triangles. Okay? And different triangulations make different pieces of the physics manifest. Some triangulations make some symmetries obvious, like in n equals 4 super Yang-Mills, or some triangulations make dual conformal invariance obvious, or the Yangian symmetry obvious. Those turn out to be related to on-shell diagrams in BCFW. Other triangulations make other things obvious. They're more closely related to Feynman diagrams. We see a very sharp version of that story for the isosahedron in a way that we'll see in half an hour, is that literally you have one triangulation, one class of triangulations of the polytope makes some hidden symmetries of the amplitude obvious. Another set of triangulations are literally Feynman diagrams. And they're related by triangulating dual things, as I'll explain in just a second. Okay, but that's one sort of big picture point, is that different triangulations of these geometries make different features of the answer obvious. And there are even qualitatively different triangulations. This is now coming to Lance's point. There are qualitatively different triangulations, some of which triangulate the object, and the others triangulate the sort of dual object. Okay, so let's talk about it in this example. Yes. Yes. Yes, the sum of the forms is the form of the square. And in fact, and you can see that it'll give you some interesting numerator, right? Because if that's right, it's a form everywhere, exactly. And again, why is it the form everywhere? Because we can check what is it, sorry, you're right, I should have finished the argument. If I sum the forms, what is the residue of the form here? Well, the only one that has that guy is this, and so we're just gonna get the canonical form of 1, 2, correct. Okay, what about 2, 3? This only has it, so we'll get the canonical form for 2, 3. What about 3, 4? This one has it, so we'll get it correct from there. We'll get it correct from there. The only place it could go wrong is in the middle, and in the middle they cancel. Okay? So that's why if you add the canonical forms for the pieces, you get the canonical form for the whole answer. And you can see that if one of them has 3 of the poles, the other one has 3 of the poles. If you combine them together under one denominator, you'll get an interesting object. Sorry, and I said it wrong. Actually, this is exactly the point that I want to talk about. So if I look at the form for this guy, not being too precise, there's some overall normalization in front. But one of them has like L12, L23, and this L31 that I'm gonna highlight. And the other one is 1 over L34, L41, also L31 that I'm highlighting. Okay? Now, why am I highlighting these guys? Because those correspond to poles that are not there in the actual answer. Okay? That's the whole point. Okay? So these are spurious poles that are absent in the actual answer, but are there in the pieces of the triangulation. Right? And that's inevitable when you triangulate the object without adding any new vertices. So if we just take the vertices as given and triangulate, we're inevitably going to introduce boundaries that are not there. Okay? Now here's another way of triangulating. Let's go back. I'm going to now triangulate in a different way. Let me do it like this. Oops. Yes, there was a question, yes. They're absolutely normalized because, sorry, I should have said it all the way back here. There's a normalization in front of everyone. By definition, when you go down to a point, you're supposed to get 1. Okay? And that's what normalizes it all the way up, because it's recursively defined. Okay? Okay. All right, so here's another kind of triangulation that we could do. So there's my quadrilateral again, but now I'm going to think of this quadrilateral as this big triangle minus this little triangle. Okay, so if this is L12, L23, L34, L41, then I could have a big triangle of L41, L23, and L34, and another triangle of L12, of L41, L12, and L23. And if I take big triangle 1 minus big triangle 2, that's the same as my quadrilateral. So this is what Lance wanted us to do. Okay? So we even see we need a sort of minus sign here. See, now each piece only has physical poles. I mean, the poles that the actual quadrilateral has. Okay, so this is a sort of a different triangulation. It's an external triangulation. The other one is kind of an internal triangulation, and it involves vertices and no new lines. This is an external triangulation. It involves no new lines, but it introduces a new point. Right? That is a new point that was not there. All right, so these are sort of two different kinds of triangulation. And in fact, there's a natural sort of way of thinking about these two triangulations, because there's a natural notion of a dual of a polytope. And if this was a longer lecture series, I'd really properly define it. But for the moment, we just need the sort of intuitive thing at the level of pictures. A dual of a picture in 2 dimensions is just a picture where everywhere you have a point, you turn it into a line. Everywhere you have a line, you turn it into a point. Okay, that's just the plane duality of Desargues going back to the 1500s. It's the most basic duality in projective geometry. But what that means is that if I have this picture where I have 1, 2, 3, 4 as vertices in L12, L23, L34, and L41 as edges, I'm going to draw a different picture. This is a dual picture where 1, 2, 3, 4 are lines. Okay? And L12, L23, L34, L41 are points. Okay? And so a cool thing is that if you give me a triangulation of the dual, it also gives me a triangulation of the original one. So let's say I take this guy and I triangulate it like that. So what do I have here? I have a triangle whose vertices are at 4, 1, 1, 2, and 2, 3, and another one which are 4, 1, 2, 3, and 3, 4. Well, that's exactly like one of these big triangle minus little triangle things if I draw it back here. Okay? So I can naturally get triangulations with vertices. I can get external triangulations where I introduce new points. And sorry, here I've introduced a new line in this picture, but this new line is a new point. Dually a new point, okay? Precisely as we talked about. Now, in fact, you can do something else even. And this is actually a very general strategy that triangulates huge classes of, it certainly triangulates polygons, it also triangulates huge classes of polytopes, including the ones that will be of interest to us in a bit. You can just put a point in the middle here. Let's say put a point in the middle in this picture, and I'm going to triangulate just by making the sort of pizza slices. Okay. Right, that's also a triangulation. And you can clearly do that for any polygon. Put a point in the middle and you'll get an n-gon, you'll get a sum of n pieces. Now, what does this triangulation look like back in the original space? Putting a point in the middle means putting a line outside. And what are all these triangles? You see, it's pretty cool. It's an inclusion-exclusion kind of a triangulation. You go to every vertex, and you look at the edges that meet at that vertex, and you just extend them to a triangle. Okay? So that's one giant triangle associated with that guy. This is a smaller triangle associated with that guy. This is another triangle associated with that guy. Yeah, and I just stop where they intersect this line. Okay, and finally I have this triangle. Okay. And so you see that the quadrilateral is the big triangle minus this little triangle minus that little triangle, and I took away this little triangle, so I have to put it back. Okay? Yes?
So in the diagram you show that the lines are intersecting, right? On the left here.
Yeah, let me draw. The challenge of this business is drawing things so they actually do something generic. Okay, so let's actually I think that this is. Yeah. Let me do it like that. Okay, so what I'm saying is that, and you draw any old line you like here, then you have this big triangle. Then you have this triangle. Then you have this triangle. Okay, so the big quadrilateral is the big triangle minus this one minus this one, and add back in this one. They're all anchored to the same line here. And so it includes that region, because when I minused that region, I took away a little bit of that part, so I'm putting it back in when I get that, in order to what I'm just be left with to just be the quadrilateral. Okay? And this is all guaranteed to work. It's just we're more visually used to seeing it on this side as a point in the middle and drawing the pizza slices. But I want to emphasize that this thing that's a point in the middle and making the pizza slices is something that involves something at infinity, a line at infinity, and a triangulation which associates a triangle with every vertex of the polygon. And in general, for when does this work? If you go to higher dimensions, it works whenever the polytope has the property that at every vertex, locally it looks like a simplex. So locally, if you're in n dimensions, locally there are n facets meeting at that point. So that means that locally it looks like a simplex, so that if you put a plane far away somewhere, you can make a tetrahedron out of every corner, out of every vertex. Okay? If you then sum all those tetrahedra with the plus and minus signs, you're guaranteed to get to cut out the polytope. So polytopes that have that property that locally at every vertex they have n facets meeting there are called simple, and that they'll be important in another. They'll be important momentarily. Okay, so summary is that at least when we have polytopes, and more generally as well, but here we're just talking about that case so far, we can triangulate these polytopes in lots of ways, and in fact, morally, there are triangulations that are natural for the polytope. There are triangulations that are natural for the dual of the polytope, and these are all, of course, all different formulas. But in the context of physics, we'll find that these are really formulas that have physical meaning. Okay, so in the case of the amplituhedron for n equals 4, if you triangulate in the simplest case of NMHV tree amplitudes, the amplituhedron is a polytope. More generally, it's a curvy polytope, but in that case, it is a polytope. And this sort of these obvious triangulations that don't introduce any new vertices, but introduce new internal boundaries, are formulas that have lots of spurious poles when you cancel them all. And what does that sound like? That's BCFW. Okay, so BCFW are triangulations of the amplituhedron. Triangulations of the dual amplituhedron are the local forms of the amplitudes that are, for example, what you get from the CSW rules. Okay, so the closest we can get to Feynman diagrams. And there you have this sort of point star that we put in the middle there. And when you do Feynman rules, a la CSW, there is some reference light-like direction, that's that star. Okay, so you get different formulas in that way. Oh, sorry, I said it wrong. CSW is actually, sorry, I apologize. The other formulas are formulas that we don't know a totally systematic way of getting them, but there are local expansions for the NMHV amplitudes. Okay, there are local expansions for the NMHV amplitudes. They don't have any poles. What gives you CSW is if you do something like BCFW, but you now put a general point star. Okay, you don't triangulate directly with some of the points that you have, but you put a point in the middle of the polytope. Anyway, we'll talk about that a little bit more in detail later. Okay. So that was just an invitation. But one thing that you're going to take away from here is that the poles or the singularities of the amplitude or of the form, they are reflecting the facet structure of the positive geometry, sort of almost by definition. And if we're going to correlate these with forms, we mean that poles and singularities of the amplitude are going to be reflected somehow in the facet structure of the corresponding positive geometry. Okay, just repeating here. Now, let's say we're working at tree level. What's the most important feature of the poles and singularities of the amplitude? The most important feature is factorization. So, broadly, locality is reflected in the fact that the amplitudes have a singularity when a sum of the subset of the momenta go on shell. So those are the only kind of singularities we can have are poles. There are poles when a sum of the subset of the momenta go on shell. And unitarity is reflected in the fact that the amplitude should factorize as 1 over this p squared minus m squared times the product of two lower point amplitudes. Okay? So if we're looking for some kind of structure in kinematic space that's going to tell us about amplitudes, already even at tree level, then it should know why the poles look like this. They involve sums of consecutive momenta. I mean, they're 1 over p squared, 1 over p squared minus m squared. They're not 1 over p squared q squared minus r squared t squared, okay? They're just things like 1 over p squared. And secondly, they have to, even more strikingly, they have to tell us that the object is sort of splitting into the product of two lower objects of the same type. Okay, so that's one of the 0th order mantras in this business, is that we're looking for the kinds of mathematical structures in the Platonic world of ideas that have this property. There are a set of objects that are indexed by some n that counts the number of, that's going to be the number of particles, but it needs to have the property that when you go to the boundaries of this object, you don't get something brand new and crazy that you've never seen before. When you go to the boundaries have to factorize into the product of other objects of the same type that you've seen before. And that should be a feature of the geometry. Now you see, if I told you that you have to somehow think of some whiz-bang mechanism, imagine that you're an experimentalist that was just measuring these amplitudes, never mind that you're measuring cross-sections. Imagine you could directly measure these amplitudes, and you imagine that you're moving the knobs around of the momenta, and you find they have poles somewhere, and then you make very careful measurements and see that they factorize into the product of simpler things that you've seen before on those poles. And you went and you told some theorists at a conference, if one of them was named Feynman, they would say, I know what's going on. That's some of Feynman diagrams that I just named after me, right? And naively, it just looks like, what other way could you do it? How else could you possibly have the poles look like this and they factorize into pieces? So the adventure of this business, very broadly, is to find new structures that for their own private reasons, they've never heard of Feynman diagrams or particles or anything like that. For their own totally private reasons, they do that. They give you spaces that when you go to the boundaries, they factorize into simpler things of the same type. If we find some new ab initio set of ideas, and perhaps someday we'll find the most general, grandest set of ideas of this sort, which give you this kind of property, then you see it's guaranteed that if the way you interrogate these objects, if the way you extract some sort of physics out of them is by asking for their canonical form, now you see the canonical form is going to do what you want at the level of the amplitude because the geometry does. Okay, because the geometry factorizes into the product of two pieces, then if a form has singularities on this guy, then, and when you go on the boundary it's a product of two lower guys, then so roughly, at least, you should expect that function that's associated with this form should also factorize in the same way. Okay? So this is one of the avatars of the looking for new principles of this business. If we can find these kinds of interesting geometric structures, as we'll see, the word geometric, anyway, if we find these interesting geometric structures that have this self-factorizing property on their boundaries, then we're close. We have an opportunity to look for some way to ask a question of that structure whose answer we'll interpret as an amplitude that depends on a bunch of momenta. But this basic fundamental fact about the factorization of the structure will turn into factorization of the amplitude. And in that way, the locality and the unitarity will be outputs out of this object rather than inputs into what went into it. Okay, so that's the kind of thing roughly we're after. Yes? Thank you. Okay, now this is something that we understand well for, well, let me just say it in words because we're not going to need it that much today. But you have this form, and there's a canonical way to strip off the dx dy part of the form. There's some overall normalization, but never mind. There is some basically canonical way to strip off the dx dy part of the form. So we have a form, but it's dx dy times a function. Okay, that function is can be interpreted as the volume of the dual of the polytope. Okay? And I haven't told you exactly what the notion of dual is, and to define the notion of a dual, you need some notion of all of this makes much more, is best phrased in the language of projective geometry. So I could explain it. We could explain it deep into the night. We can explain all these things. But at the moment, roughly all you should know is that there is this, it's kind of cool that this canonical form sort of looks like a volume, but it isn't a volume, it's a form. Okay? And you can add them. They have a lot of the same sort of additive properties as volume does. But it's not itself a volume. However, it is, if you strip off the form part, the function part is a volume, but it's a volume of the dual polytope. That we know for polytopes, and we don't yet know how that works for these Grassmannian generalizations of polytopes in the amplituhedron. And that is the white whale of this business for those of us who think about the amplituhedron, is we're sure this dual of the amplituhedron exists, and it's giving us all kinds of hints for 5, 6, 7 years now that it exists, but we don't know how to describe it yet. Okay. So, that was all just to motivate that once we find shapes, this is what we're going to do to the shapes to get functions that we'll then interpret as the amplitudes, okay? So now what I want to do is switch to talking about what these interesting shapes are and where these interesting shapes are arising in kinematic space, okay? So now, part 2, I want to talk about the sort of polytopal structure in the pattern of how poles come together. Okay, so again, this is another little vignette, but let's go back to our friend, the experimentalist, who is measuring a bunch of amplitudes for spinless particles, okay, so scalar particles, and there's an ordering, there's a sort of color ordering for them. So secretly, this is coming from a Lagrangian, which is trace d phi squared plus g trace phi cubed. And phi is an n by n matrix. Okay, so really, I would draw at tree level, I would draw these diagrams like this, or like this. Okay, this is the sort of double line notation for the colors, but I'm not going to draw them in. I'm not going to draw them that way anymore. All that matters for us, we're just still be working at the tree level here. All that matters for us is that the indices are ordered and we're only drawing planar diagrams. So at 4 points, I would just have this diagram. So these would be the S and the T channels. At 5 points, we have these 5 diagrams. At 6 points, we have more topologies. And Mercedes-Benz. And so on. Okay, so we have a bunch of diagrams like that. All right? Okay, so that's secretly what's going on with this experimentalist doesn't know that that's what's going on. But they notice that the amplitude blows up when some of the kinematic invariants go on shell. When some of the kinematic invariants are, when they go on shell. So before doing anything else, let's actually first talk about what the kinematic invariants actually are. So the only invariants these amplitudes depend on are Mandelstams. And so if you have n momenta, let's say n null, but they just have to be on shell. Okay, so if you have n massless, but just for simplicity, let me say they're massless, doesn't matter. It's just scalars. N massless momenta, naively, I have n choose 2 invariants, right? Pi dot pj. Remember, all the pi squared are equal to mi squared. Either 0 or mi squared, they're locked, so that they can't vary. So there's naively n choose 2 invariants, but I have momentum conservation that says the sum over j of pi dot pj is equal to 0, if they're massless. So that means that I have n choose 2 minus n, which is also nn minus 3 over 2 independent Mandelstam invariants. Okay, so that's just the first thing to know. So this is our kinematic space. One way of talking about our kinematic space is it's this nn minus 3 over 2-dimensional space. You could say it's a space of these dot products pi dot pj up to this constraint. Or you could solve the constraint by solving for a bunch of them in terms of a subset of n choose 2 minus n of them. Okay, yes?
Those Feynman diagrams that you wrote,
Yes.
they would be there even if I wrote an off-shell amplitude.
Yes, that's right.
So this combinatorics,
Yes,
when we define it in this kinematic space, which is on-shell,
yes.
is it just that for on-shell we are able to factor out the combinatorics more easily, or is it that there is a richer structure?
No, there's something very important about being on shell. You see, it's not that I have, it's very important that it's, that the p squareds are not treated as variables. Okay? If this is a totally generic correlation function, then I would care about the dependence also on each momentum. Okay? Then I just have more variables. Okay? That's a really crucial thing in this whole story. It doesn't have to be massless, but it does have to be on shell. Yeah.
There's still this combinatorics.
That's right. There's still the combinatorics. There's still all the combinatorics, but the sort of structure that we're going to see, and you know, there are steps going beyond amplitudes. The kind of first step beyond amplitudes is that just introduces a single new variable, is correlation functions where all the points are on an equal time surface. And these are the things that are relevant in cosmology. They're cosmological correlators. And these guys are almost amplitudes. They introduce a single variable beyond amplitudes. And so we can start taking these steps beyond amplitudes. We're talking about form factors, talking about insertions of extra points and so on. But there is definitely something about the on-shellness that matters a lot, even in these scalar examples, okay? So it doesn't matter that it's massless, but it will matter that it's on-shell. Okay, so now there's a much nicer way of thinking about these invariants. Let's look at this sort of a famous polygon of momenta that you've probably seen many times, and we'll even come back to again later, where we draw the momenta n to n, p1, p2, p3, up to pn. And momentum conservation tells us that, that we get a closed polygon out of this. The sum of all the p's is equal to 0, so that gives us a closed polygon. And then it's very natural to look at the distance squared between any 2 points, I and j. So let me define xij to equal pi plus 1 plus dot dot plus pj minus 1 all squared. Okay, so that would just be exactly the distance squared, because that's pj minus 1 here. Okay, that's pi, that's pj minus 1. Okay, now, first of all, these xij's are special for 2 reasons. One of them is that they're exactly the poles that occur in these planar diagrams. Okay, so these are exactly the poles of the planar diagrams. Right, so for instance, if I look at okay, if this is 1, 2, 3, 4, 5, 6, who is this momentum? It's P1 plus P2. This one is P1 plus P2 plus P3. Okay? Or, of course, I could think of it as minus P4 minus P5, but it doesn't matter. The momenta that we see are always sums of consecutive momenta, right? That's the sort of key thing. And so all of these xij's are precisely the poles of the planar diagrams. So that's very nice. Any diagram is just the product of a bunch of 1 over x's. That's the first thing. But the next thing is, how many of them are there? Well, there's exactly n choose 2 minus n of them. Exactly the same number as the number of invariants. Okay? Because I have n choose 2 would be all possible edges, which includes the boundary edges, but xii plus 1 would be pi squared, and that's exactly the guys that are locked. Okay? So the number of interior chords of this polygon is exactly the number of Mandelstam invariants, so this is also a basis for all the Mandelstam invariants. Okay, so this is now our kinematic space. No. Any one diagram only has some of the poles. But the only poles that we see in any diagram are one of these guys. Okay, in fact, I'm going to just come to a moment to think about the diagrams in this language. Okay, so let's say, good. So let's say we take this diagram, the one that I just erased unhelpfully, and let me draw its corresponding polygon. So let's indeed see who are the momenta, who are the poles that we see in this picture. So we see like P1 plus P2 squared. By the way, there's already this slight annoyance here. Do I label it P1 plus P2 squared or minus P3, minus P4, minus P5, minus P6, right? Of course, they're the same, but it's slightly annoying. Which way do you describe it? Well, let's see what it looks like in this picture. Who is P1 plus P2 squared? P1 plus P2 squared is that line, right? And now that's very nice because now it doesn't matter. It's symmetrical between the left and the right. Okay, it's just so this is just x13. Okay. Who is this one? Is P1 plus P2 plus is P1 plus P2 plus P3 squared? So that's that one. That's x14. And who is this guy? Is P4 plus P5 squared? So that's that one. So that's x46. Okay? So already we see that we can either draw Feynman diagrams, or we can draw what? A triangulation of the polygon. Okay? And so another way of writing the amplitude is the sum over all triangulations of the n-gon, T, times, for each triangulation, the product of all the chords ij in the triangulation of 1 over xij. Right? So this is another way of just writing the tree amplitudes for this dumb theory. Okay? But anyway, that's secretly what's going on behind the scenes, but the experimentalist doesn't know any of this, but they have their finger on the xij dial. Those are all of the invariants there are. It's the basis for all the invariants. They have a finger on the xij dial. So what do? Well, they're moving the xij's around, and poof, when some xij is 0, the amplitude is a pole. And what they do after this, I've made this joke many times, so if you've heard it before, I'm sorry, but I can't resist making it because I have so many experimental particle physicist friends, I like to bug them. How you respond depends on the kind of experimentalist you are, because there's some fraction of experimentalists who really wanted to be theorists. They're very disappointed they couldn't be theorists, okay? And they know who they are, so I won't call them out. But if you're a closet theorist experimentalist, then you're like, ooh, there's a pole here. Poles are cool. I care about residues. I'm going to measure what's happening in the neighborhood of the pole and call it a residue, and then maybe the people at the conference will think I'm secretly a theorist. Okay, so and that's great. And if they do that, they discover something amazing. They do some very careful measurements in the neighborhood of the pole, and they discover, wow, in the neighborhood of the pole, the amplitude factorizes into the product of two lower things I've seen before. Very exciting. And then Feynman's in the audience and says, oh, and there's Feynman diagrams that I named after me, right? So in other words, if factorization is the star of the show, then you're immediately going to thinking about Feynman diagrams as what's going on. In fact, if there's another theorist in the audience who is less famous a physicist than Feynman, but a greater intellect in many ways, and his name is Pierre Deline, Pierre Deline would say something entirely different. He says, no, I've seen that before. I've seen it before that there is some structure that when you go to some boundary, it splits into the product of two other things. That's just what happens in the simplest moduli space you ever talk about in math of just endpoints on the boundary of a disk or endpoints on P1. And, oh, your physicists maybe haven't heard of this, but this is the first thing you study, you know. Geometry 101 is that the boundary structure of the space splits into smaller spaces of the same type. Okay, so Feynman's like, God, I've never heard of that. He's like, yeah, this is something else which does that. And if you pursue that, there is another formula. There's another way to kind of dress the structure with a formula that gives you amplitudes out of that, and that's called string theory. Okay? That's the simplest example of the open string worldsheet. And the reason why the open string theory gives you the right answer is this fact about the moduli space of endpoints on the boundary of a disk. Nothing to do with Feynman diagrams. It's a different fact. Okay, so in many ways, string theory is a kind of first example of a slightly unfamiliar structure in a different place that does the same thing, that gives us factorization on its boundaries. And then you sort of interrogate it with a different kind of question, and out of it you get amplitudes. Okay? But what I want to stress is that if factorization is the star of the show, what you discover are the two ways of thinking about particle scattering, one way or the other, that have dominated our thinking for 60 years, 50, 60 years, 70 years. Particles or strings, okay, but maybe most familiarly particles. Okay, but I wanted to make this comment about the strings anyway. Okay, now, but what if you're a much lazier experimentalist? So the hero of my story is a much lazier experimentalist, but much smarter one. And these are experimentalists who don't give a rat's ass about theory. They hate theorists. Experimentalists like this used to exist. Maybe they still exist, but they used to be more proud of it back in the day. And I love them. Lots of fun talking to them. Lance remembers at least one of them, but he didn't really hate theorists. I don't know if Bert hated theorists, but you know, Matthew, you're personally responsible for making them hate theorists. No, you're not. Okay, so this person says, look, I see that we hit poles. Poles are exciting. Poles are cool. I make the Mandel-Simon variance move around, I hit a pole. Can I get a second pole? They're like a little kid. They want to make it blow up even more, right? So that's all they do. They don't do any detailed measurements. They don't know the word Cauchy. They don't even know what I is, okay? So, all right? They're the hero of my story. So what happens if you do this? And from now on, I'm going to draw what's going on behind the scenes in terms of the Feynman diagrams, but I'm going to draw it in the language of the triangulation of the polygon, okay? So remember, the triangulations of the polygon are just dual to Feynman diagrams. Actually, maybe before going further to the story, let me just say, what if we, let's start with this. Let's go back to this hexagon. What if I just drew this, okay? What might you sort of reasonably think of if I just drew this? This is just one pole, right? This is just, and so you can actually reasonably think of this picture as actually giving you the factorization of the amplitude on this pole. So I should have said this before, that if a given xij goes to 0, the amplitude is going like 1 over xij, but multiplied exactly by the product of the two subpolygons that you would get if you cut exactly along ij. Is that clear? So in the language of the, I'm just translating, but when we say that on the pole you get the product of the blob on the left and the blob on the right with a line in the middle, in the language of the polygon it says it's 1 over xij, and then you get the amplitude for the polygon on the left times the polygon on the right. Okay? So this is the fact that so excites experimentalist 1. Experimentalist 2 doesn't care, okay? But they notice something interesting. Like, let's say you just have 4-point scattering. Then you can have a pole when x13 goes to 0. And don't ask me what signature we're in and so on. Okay, if we're in Lorentzian signature, there are constraints, so you can't actually access all possible Mandel-Simon variants. This is actually a separate, very interesting point. But let's, this is a very imaginary experimentalist who's like living in split signature, and they can have all possible values of the x's, okay? So, but they notice that if x13 goes to 0, the amplitude has a pole, but that's it. Then they can do x24. Anything they do with x24, no more pole. Or the other way, x24 can go to 0, but then anything they do with x13, no more pole. And, well, why is that? It's because, you know, there is no process that has both of these propagators at the same time. There's no local process that has both the S and the T channel poles at the same time. Or if I say it more visually in terms of this polygon, I can't have crossing chords. If I have crossing chords, there's no local process that has crossing chords in it. All right, so they then notice that at 5 points, the situation is a little bit more interesting. They notice that, let's say, they could have a pole when x13 goes to 0. They can have a single pole when either x13 goes to 0, x24 goes to 0, plus cyclic, x35 goes to 0, and so on. Right? But they could also have two poles, double poles. So when x13 goes to 0, they can also put something else to be 0. So let's say x13 has already gone to 0. They can also have x14 goes to 0. Or they could also have x35 goes to 0. But not any of the other ones, not x24, not any of the other ones go to 0. These are absent. And again, let's see why. Again, secretly in the language of the pentagon, when x13 goes to 0, who are the other poles that I can have? I have to draw another chord that doesn't cross this one. Okay, so I can draw this one, or I can draw this one, but I can't draw any other ones. Okay? So you see there's an interesting pattern, but if you don't draw any pictures or anything, you just give a list. Say, here are the list of all the single poles, 1, 3, 2, 4, 3, all of them. Here are the lists of the double poles. Okay, there's an interesting list. It's not every possible combination. There are some interesting lists in how the double poles come together. And you could either present this information as a boring list at your Moriond in 2-2 signature, okay? Or you try to present this data in a more vivid way. So can you sort of capture, how could you capture the pattern in which all the poles come together? The single poles, the double poles, all of them. And you can capture it by the following beautiful picture. It's completely coincidental that it's a pentagon again. We'll see the fancier version of it in a second. I keep losing, it's this thing. Okay, it's a pentagon again. This is a completely different pentagon. And I'm going to think of like this edge of the pentagon. This edge is going to represent single pole. And this edge is going to be, let's say, that single pole. Okay? Now, the vertices, so this is going to be some other single pole. I haven't drawn who it is yet. We'll figure out who it is in a second. But the idea is that all of the edges, all the codimension 1 boundaries, all the edges correspond to a single pole. All the codimension 2 boundaries are those single poles that can come together, which means that we're finding a shape where if the faces meet, that means that that collection of chords can come together. That collection of poles can come together. Okay? We want to see, is it possible to draw a picture? Not at all obvious ahead of time, but here it's simple enough that we can do it. So let's see. So the vertices would have to be 2 guys coming together. So let's say, which 2 guys could it be? Well, I'll make a choice on this side. I'll say it's that one. Okay, but then that immediately tells me who is this next guy, right? This next guy is then got to be that. Okay, and so on. So you can keep going around and decorate the rest of this picture, and it works. So is it clear what we've done? We've captured, and notice it's not the most trivial thing you might have imagined. The most trivial thing you might have imagined is that you start here, and then maybe you cyclically rotate these chords over. But it's not cyclically rotating them, it's rotating them by 2. As you go from here to there, it's rotating them by, it's cyclically rotating the picture by 2, from here to there. Okay, so you go around. Okay, so, and so this guy would be this one, and that one, and so on. Okay, I'll leave it to you to fill in the rest of them. All right, so that's kind of interesting, So this is for n equals 5. So for n equals 5, so what we're seeing is that the pattern of poles, the pattern of how the poles come together has a shape, is captured by a shape. So if we do it at 4 points, and just by convention, you can sort of think about the interior as no chords at all. So the interior is like the generic amplitude. This is the first factorization, the complete factorization in this case, okay, where you keep putting on poles. What about at 4 points? This would be the interior, this would be the S channel, this would be the T channel. Okay, now here it was easy enough to sort of guess that there's a shape, but yes?
Yeah, I was wondering if we really need to do this to find results. If we really need to apply these pictures to find how the poles come together. If I write like a three-level diagram, I could find it in the same way, right? So,
right, except what I'm saying is that the lists of poles are exactly the same. I'm telling you something about the pattern in which and how these poles come together, which is not obvious a priori, just giving you that list. So I want to say there's a fact about how these poles come together, which is not in all the textbooks. Okay, so it's something very basic, just about the sort of combinatorics of how poles can come together. That's reflecting something about space-time locality. It's just locality, right? With just locality. The things that are forbidden are the things that don't correspond to local space-time processes. Maybe it'll be more interesting when you see the next example. And in fact, if you haven't seen this before, if you have seen it, you know what the answer looks like. But even if you have seen it, it's worth sort of thinking what you would do if you didn't know. So let's say you want to look for an analog of this picture at 6 points. So first of all, what's the dimensionality of the picture that we're talking about? How many poles can we have? 3. So the answer is n minus 3 poles for n-point scattering. We went 1, 2, 3 for n equals 6. We saw that in the triangulations. All the triangulations had sort of three chords inside them. So we're looking for some kind of three-dimensional picture. We want a three-dimensional picture where the vertices would be triangulations, complete triangulations. The facets would just be one line, and the edges would have to be 2 lines, right? And at the most coarse basic level, let's say you wanted to check, is it even possible to dream that there is a shape where can you see it's not trivial. I need to draw a three-dimensional shape. I need to have the number of vertices of the shape has got to equal the number of complete triangulations. The number of edges of the shape has got to equal the number of partial triangulations with just 2 guys in it. And the number of faces would have to equal the number of just single guys, right? So is it possible? Is it possible that there is something that captures in a shape such that I can decorate all the vertices, facets, all the facets, edges, and vertices with partial triangulations of the hexagon in a way that if 2 facets meet, that means that the chords are compatible with each other. Now, let's do first a very basic check. Very basic check. Is just count how many of them there are. Okay, so, and I'll just tell you what the answers are. Well, this one's really easy to count. What is the number of single lines? Is just our n choose 2 minus n, right? So that's just the number of propagators. So this is equal to 9. Okay? So there are just 9 nn minus 3 over 2. 6 times 3 over 2 is 9. What is the number of diagrams? That's also not so hard to count and see that the answer is 14. Okay? And you can then just go count, manually count how many of these there are. And this you discover is 21. Okay, that's just from counting, right? Just count how many of these things there are. There's a formula for any n where you can count how many of these things there are at any level, and is given by some interesting hypergeometric function evaluated at integer values. Not a trivial formula. Okay? You get some generating function. There's some interesting formula that gives you these counts. I forget the numbers at higher n, but it's not some sort of dumb, obvious formula. You have to do a little bit of work to get these numbers. Okay? But now let's look here. Is there a prayer that there's a shape that has 9 facets, 21 edges, and 14 vertices? Do you know some check that you can do? Exactly, Euler's formula, right? If there is a check, if there is some kind of nice polyhedral ball-like structure, then it has to have that v minus e plus f is equal to 2. And v minus e plus f is equal to 2. Okay? But I want you to see this now is some interesting fact about how these numbers worked out. And if you do these v minus e plus f's for the other cases, it's always the correct number. 0 when you do it properly, right? When you define it properly. The Euler characteristic is always 0. And that's some interesting identity about hypergeometric functions. That from the direct counting, it's not at all obvious that this should be the case. But it's true. Okay? In fact, there is a shape. And it was first discovered by Jim Stashev, the mathematician Jim Stashev in the 1960s. And it's called the isosahedron. And I'll draw what it looks like in the 6-point case. And I'll actually leave it to you as a nice exercise to fill in everything. I'll get you going. Okay, so this is what the shape looks like. You see, it has 6 pentagonal faces and 3 square faces. The 6 pentagonal faces are this one, this one, this one, this one, the one on the back, one on the other side. Okay, and the 3 square faces are this one, and that one. And I'll get you going. I mean, you'll also see it, on Wikipedia. But these 2 special points, like this is one of the, if I think of this as a triangulation of the hexagon, there's the sort of up and down points are sort of clearly special, and there are the 2 Mercedes-Benz diagrams. So these vertices are that one and the other one. But now I invite you to go in and fill in, just try to do it yourself. Fill in all the rest of the vertices and the edges and the facets with either single lines, double lines, 1 chord, 2 chords, 3 chords, in such a way that everything is consistent. Okay? That when 2 faces meet, it means that the corresponding chords are compatible with each other. So that the lower dimensional object is just is a refinement of the coarser triangulations that you get from the higher dimensional ones. Okay? I can do it for you, but I don't want to spoil your fun. Now, in fact, so this is not such a trivial shape. The way I've drawn it, it's sort of clearly polytopic. All the edges are flat. Okay? Just to give you an idea, when Stashev did this for his PhD thesis, and he actually only realized that it was a ball. So he knew that satisfied this Euler characteristic property for any n, but he did not know that it was actually polytopic, that you could cut it out with flat inequalities, that it looked like this. And the story is that his thesis advisor actually brought a cardboard cutout of this shape to his thesis defense, okay? Just to make it clear that something existed, but it wasn't until the 1980s that mathematicians figured out what this looks like for general n. But there's really an honest polytope that captures exactly this stuff. All right, so this is a fact about how poles come together. It's a fact about the pattern in which poles come together. It's a fact that's deeply connected to space-time locality, that the pattern in which they come together has this sort of polytopal property. It's captured by a polytope, right? So that's a fact that we all know about factorization in the textbooks, but we don't know about this fact in the textbooks. Now, what's interesting is that this actually also knows about factorization. This knows everything we knew before. It also knows more, okay? But why does it know about factorization? And here we see already, more concretely, some of the general philosophy we were talking about before. So factorization means what happens when you draw one chord, right? When we go to a pole, that means that we're going to a face of this, a facet, codimension 1 facet of this object. All right, now what do these facets look like? Well, we just said there are 6 of them look like pentagons and 3 of them look like squares. But the general statement is if you look at the boundary, this is meant to be boundary operator, any boundary of the endpoint amplituhedron, isosahedron, sorry, is actually the direct product of 2 lower isosahedra. With n is equal to n1 plus n2 minus 2. Exactly what you'd expect from the exchange particle picture, okay? Just from the factorization picture, right? But let's see how it works in this case. So, so first of all, let's list who are all the isosahedra that we've seen so far. So for n equals 4, the isosahedron was an interval. For n equals 5, the isosahedron was a pentagon. Now, we didn't actually say it. What is it for n equals 3? It's a point. It's a zero-dimensional space, it's a point. Okay? Who are these 6 guys? These 6 guys are exactly what in normal amplitudes language we would talk about as a 5-point times 3-point factorization, or in the language of the hexagon is just one of these guys, right? So who are we supposed to get here? We're supposed to get a triangle on one side and the isosahedron for this on one side and the isosahedron for this the other side. That's a point. The isosahedron for 5 points is a what? Is a pentagon. So that's exactly correct. These pentagons are exactly 5-point times 3-point. Okay. What about the other 3 kinds are this kind of guy, right? What are we supposed to get here? We're supposed to get the isosahedron for 4-point times the isosahedron for 4-point. What is the isosahedron for 4-point? It's an interval. What's the isosahedron for the other 4 points? It's an interval. What's the direct product of 2 intervals? It's a square. Okay? So this is pretty amazing, right? There is something super basic in the pattern of how the poles come together. They're captured by a polytope. For some reason, we'd like to understand where this polytope comes from. Why? That's what we'll start with when we finish eating. We'd like to understand where it comes from, but I want to stress that this object, where does this object exist? In kinematic space. Just exists in the space of xij's, right? You know, just in the space, but there's something interesting in the pattern of how these poles come together that's captured by a polytope for some reason. The polytope, that fact was not sort of known in all of our books, but this polytope also has another property that on its boundaries it factorizes the product of other polytopes of the same type. So now what we're going to do when we come back, so this is an invitation. This is an example of the kind of structure that exists in kinematic space that we now have to explain where does it come from. Okay? We want to find some questions in kinematic space whose answer will be the isosahedron, and to tell us where this came from, right? And then see where that leads us. And that's what we'll begin with. Okay, thanks.
Okay, excellent. Okay, well, the pizzas are ready in the back, so I guess we postponed the questions and discussions to the break, and we will meet in here back in half an hour at 8:30.
But is there other is there other chalk, Yara? Is this the only chalk there is? Are there any slightly better chalks?
Better shot than that.
No, this is okay. I'll use it. Okay. Yes.
Yeah, so for endpoints, it looks like for n particle, the geometrical structure that we'll get is like n-3 dimensional.
Yes.
Is that always the case, or maybe?
No.
there's some
I mean, it's that case here at tree level, which is all we're talking
tree
about.
level.
Yeah. In
Because
this
you can
story-
go and sit on the n-3 poles, I guess. Like
That's
for the
right.
bike pole,
Exactly.
you can
That's
sit on
right.
the double
Exactly.
pole.
And that'll tell you the sort of number of vertices in the yeah. But in general, once we start doing this at loop level, we're also going to have, hey, how you doing? We're also going to have variables for the internal loop propagators, and there'll be more variables.
I see.
And this is all kind of quite common between the story of the icosahedron and the amplituhedron when it comes to talking about the loop integrand. When we talk about the loop integrand, we have these things. There are variables corresponding to loop variables, and yeah.
And can you explain the difference? Like, okay, this is the associated. Now, what
Yes.
was supposed to be the amplitude?
The amplituhedron is for n equals 4 super Yang mills, and we'll talk, and for gluons, and we'll talk about that after we talk about this. I'm going a little slow, but the fundamental difference is that here our kinematic space is Mandelstam invariance, which involves pairs of momenta. It's labeled by two particles, pi dot pj or xij. Which is a little bit unsatisfying. I mean, really, the kinematic space is directly the momenta of the particles, directly the momenta of the particles, and the amplituhedron is going to live in that kinematic space, directly the momenta of the particles. Yes.
I had a sort of a similar question to that. So I have a very so do I understand it correctly that you have a shape and then you're doing triangulations?
Yes.
And the issue is that there's lots of different ways.
There are lots of
that
different ways
you
of
can do
doing
that, 'cause it's
triangulation.
triangulation.
Yeah.
I was wondering what if you, instead of doing triangulation, did like a tessellation where you try and look for one shape that can like tile the whole surface instead of looking for triangulations, which is harder to find. But
Well, part of the issue is that the reason why so just not to confuse things, I'm afraid this might be slightly confusing. We're talking about like a polygon as a positive geometry that we then wanted to triangulate to get the form, right? And then we have these polygons that we're also triangulating, and these have nothing to do with each other. This polygon that we're triangulating is a purely combinatorial polygon. It's a stand-in for who all the poles are. So it's just a picture, right? It's not so. So there, so tessellation isn't even the point. The point really is the triangulation that tell you what all the poles are that come together. For the other side, though, now let's go back to the other picture. You say, okay, we have these we have these regions. Why should we triangulate them? Well, one problem is that for these guys, the sort of external data of the problem is often encoded in some way in the positions of the vertices of the shape. So as you move the data around, the shape, the actual details of the shape can change. So typically tessellations have some kind of symmetry, something that's nice about the thing that you're trying to cover. So that's one issue. But a little bit more broadly than that, there are approaches to finding canonical forms that are in the spirit of what you're saying. That if you like, essentially what you want to do is find any way to map a triangle into your problem. Okay. Yeah. So one way is to take your complicated shape and cover it with lots of triangles. Another thing you do is to find some sort of diffeomorphism, some map from the interior of the triangle, one-to-one into the interior of the region.
okay.
And if you could do that, that would also give you the answer that you wanted. Okay, so, and there's a whole strategy for doing that. Okay, there are these, and in fact, the entire, from this sort of positive geometric perspective, the entire story of CHY and scattering equation, all of that is just this. It has nothing to do with strings, it has nothing to do with amplitudes even. It's just a very general fact about canonical forms that, that when you have any polytope, there is a way of starting with a positive orthant and just finding a diffeomorphism that maps into that polytope. Okay, and that if you take the and there's a very simple function associated with it whose critical points have the property that if you sum over all the solutions of the critical points, you actually get the canonical form. Okay, so that's the sort of basic sort of CHY story. Is just a special case of that very general fact that's true for random polytopes. It's just that there's an especially nice push forward from an especially nice simplex into the isosahedron, and that's the story, and that's what the scattering equation is. But that's kind of in the spirit of what you want. It's not a tessellation in terms of flat shapes, but it's a tessellation in terms of curvy shapes. It's like you take something simple and then you find a complicated map to kind of turn it into the shape you want.
Yeah.
I can give you this is a really cool thing. You can experiment with it, and then you'll see what the pattern is. Let's say you want to, let's say I want to cover the interior of this funny pentagon, and its corners are just random corners. It's D1, D2, to D5. Two vectors. Okay? Well, one thing I could do is say that all the points inside look like, and we'll talk about this when we talk about the Amplitudes get to 3 a.m. But the sort of points, all the points inside are just some positive linear combination of the vertices normalized by the sum. Right? Where these C's are positive. Okay? And that's fine, but this is a highly redundant map because there are 5 C's and this is a 2-dimensional space. So that means there's many equivalent C's to give me the same point. What would be really cool though is if you could parameterize these 5 C's in terms of just 2 variables. I want to take each C I, and I want to parameterize it in terms of 2 variables x and y. Okay? In such a way, somehow, can I do it somehow? Such that if x and y span from 0 to infinity, so positive, if span from 0 to infinity, I cover the entire interior of this pentagon.
And nothing else.
And nothing else. Okay. That's so can you do that? Right? So clearly, what would it have to look like roughly? Like locally in this neighborhood, it's probably going to look something like this. The x and y will look something like that. But see, it'll look something. It has to get sort of curvy and do some funky thing like that, right? If you see what I'm getting. Right? So as you go to infinity in x and y, you're going to approach these different regions in different ways. Okay. Now I'm going to tell you how to do it, and how to do it for a random shape, for a random volume. Super cool. To begin with, you draw another copy of your shape, but this time with integer vertices. Okay. So it has to have the same shape. In this case, it just also has to be a pentagon. But nothing about the detailed location. So I'm going to make the simplest pentagon I can. It's going to be an integer coordinate. So I'll put one of them at here. The simplest pentagon I can. Okay, so this is 0, 0, 1, 0, 2, 1. Did I do it right? 1, 2, and 0. Okay. All right. And now I'm going to give you a formula for the C1 through C5 as a function of x and y. Right? So, so I'm going to label this 1, 2, 3, 4, 5. Just the same way as I had to. It's an integer version of the same. Okay, so the formula that C1 is x, and I look at the coordinates. So it's x to the power of the first coordinate, which would be 0, and y to the power of the second coordinate, which is 0. That's what C1 equals 1. C2 would be x to the 1, y to the 0. Again, just reading it off from these y over 1, x squared y, c4 is xy squared, c5 is y. And it's just an amazing fact. You just plot it in Mathematica. Just do like region plot 2D, or just region plot. I guess you don't need the 2D, okay? And just plot this. Just plot y is equal to z1 plus x z2
That's very cool.
plus x squared y z3 plus xy squared z4 plus y z5 divided by 1 plus x squared y plus xy squared plus y. Right? And you just do it, and you'll see that it does exactly what I showed.
Thank you.
And the final piece of what I was showing him, this is literally the analog. This is literally what's happening in CHY. Literally, is what happens if you take, now, if someone told you you have this region, x positive, y positive, here, what's the canonical form associated with this region? Well, obviously, it's just dx over x, dy over y. Okay? But let's say you take some point inside here. There's a unique real value, real positive value for x and y that's associated with it. That's what I told you in this construction. However, there's many complex points in x and y associated. Right? So in other words, I've parametrized this point. I've parametrized z in terms of x and y. But what I can do is look at I can pick some z star at any point I like, and just ask for all of the x and y's such that z at x and y is equal to z star. Okay? So there's many such points. There's a bunch of algebraic equations, you see? There's a bunch of polynomial equations, so there's many such points. Okay? But if you now take this form dx over x, dy over y, this induces a form on z space, just evaluating this form on each one of these solutions. You sum over all the solutions, that's the canonical form for the pentagon. Okay, so that's the sense in which when you solve the problem, that's what I said. The sort of key thing is to find some way to take a triangle, and this is a triangle with a line of infinity, but to take a simple region and figure out how to cover your space. Yeah. The dumbest way is to just glue, tunk, put them in like Lego pieces. But there are these more interesting ways that involve these nonlinear maps. And I think for polytopes, essentially every one of these things is understood now in one way or the other. But figuring out what the analogs of these things are for the curvy polytopes is a big open problem. Okay. Yeah, but play with it. This is really cool. And if you haven't run into them before, this is the entire story of Newton polytopes is about this. Okay? And in fact, if you experiment with this formula and try to understand why it works, you'll discover everything about tropical geometry and Newton polytopes and all that stuff is actually there in this little example. You see, the sort of cool thing is, how can it possibly be that this thing that only has x and y, after all, x and y seem to only have these two boundaries at infinity, right? How can it possibly be this is going to be something that gives you 5 vertices? Or imagine I had an n-gon. How can it possibly give you something with 100 vertices? The point is that as I go to infinity in xy space at different rates, I can go in different rates in such a way that different ones of these monomials dominate. If I just go on the x-axis, then x will dominate. If I just go on the y-axis, y will dominate. But if I go somewhere in between, then x squared y could be bigger than x, but smaller than xy squared, and so on, right? So this xy space is actually just gets broken up into regions where different ones of these monomials dominate. And in those regions, y sort of screens out towards these vertices. Okay? So that sort of makes it clear that the boundaries can be covered. And then there's a very cool positivity fact. And this is a positivity fact that's very closely related to the positive Grassmannian and the positivity of the amplitude. But here, it's crucial that the shape that you choose here is the same as the shape you choose here. If you calculate the Jacobian of this map, you find that it's always positive. never goes to zero. Okay? And that's why it works. The Jacobian can never go to zero. So it's 1 to 1. The only thing you've got to worry about is what happens at infinity, and it's guaranteed to hit all the boundaries. Okay. Yeah. Anyway, this is a great example. If you don't know of all this Newton polytope tropical stuff, you'll learn all of it. If you do, then it's fun to see it as an example.
Cool. Thank you so much.
No problem. Should we get some pizza? You guys want some pizza?
I think you got your one.
Oh, this is my pizza.
Yes.
Better be good. Oh, looks pretty good.
I don't want to keep you from eating too much, but can I ask like a question? Because I'm going to have to head out now, unfortunately.
No problem, sure.
I have a flight like in 3 hours.
Oh,
Yeah.
where's home?
Oh, not home yet. I'm going to Israel first. And,
Oh, cool.
Yeah, and then Cambridge is home. So locality seems to be a big thing in this community. I'm not an Amplitudes guy, by the way, but it seems like to work beautifully in these cases. But if I think of something like strongly coupled string theory, I don't expect necessarily a space-time locality to be reflected anywhere in that answer. Is that the case? And if so, like, can that be accommodated somehow?
There's a couple of different aspects of this. There's some sense in which locality is violated in quantum gravity. But it's very subtle. It's very, very subtle. Its effects that go like e to the minus 1 over g Newton. In particular, you don't see them in any order in the... Not everyone agrees with this statement, but every sensible person agrees with this statement. You don't see this violation of locality in any order in the G Newton expansion. And it's blockaholics. It's things that go like e to the minus entropy, e to the minus 1 of area over g Newton. And they matter at order 1 for very esoteric questions like the black hole information paradox. It's an exceedingly esoteric question about what happens when you measure every single Hawking quantum that comes out of an evaporating black hole, or more than half of them. You have to do this insane measurement in order to conclude that there's a problem.
Yeah.
And and that's because there's something that's fundamentally only like e to the minus s. You have to compensate with an e to the plus s in the insanity of the question, right? So those are the kind of things where we expect there's some breakdown of locality. In particular, there's no breakdown of locality expected in any order in the G Newton expansion or in any order in string perturbation theory either.
In any order in G string?
Any order in G string.
Okay, that's
absolutely.
fair.
It's all
Sure. I think I know that.
non-perturbative. In fact, not just non-perturbative, it has to be literally gravitational. It's not even like de-instanton effects are not. It really has to be e to the minus 1 over g Newton. Okay? And this is a little counter to what people say some people say in string theory. That, oh, string theory is very non-local. We have T-duality. We have all these things that, and there are some sense, and there are some notions of, there are some kind of intuitive notions of locality where strings are clearly more extended than point particles. But there's kind of a precise way in which locality is encoded in the analytic structure of scattering amplitudes. And string theory satisfies all of those even better than field theory does.
But perturbative string theory, right?
Perturbative string theory, and